Hey there, in this video we're going to talk about errors with our numerical integrators and how we can try and minimize those errors. So the root of the problem here is that we are replacing the actual function with some kind of fit. In the case of the trapezoidal rule, we're just fitting a bunch of line segments to the function. So let's say that the actual function here got some kind of curved shape to it. And then I do a trapezoid rule. Let's say we have points at 0 and h. This would be just like the very first slice. Connect the dots. And of course, we're calculating a different area. What we have here is in the space, we have some error compared to the integration that I'd end up calculating. And the way around this is you divide your interval up into many regions. And so that in each individual region, you have just a small amount of error. And sometimes your trapezoid rule ends up underneath the curve, like in the picture I just sketched, the black line was under the red, and sometimes it goes over the curve, and you hope it more or less cancels out. Okay, so let's estimate how many steps we need for a given error. So here's our integration, 0 to h of f of x dx. Generically, this is the integration from a to b, but when we're talking about error, it doesn't really matter where along the function I'm doing this. It's just sort of a general order of magnitude problem we have anywhere along the curve. So this will make the math just a little bit cleaner if one of our limits can be 0. So think of this just sort of like the first slice. And if we look at what that gives us from the trapezoidal rule, we'd have h on 2 times f at 0 plus h on 2 times f on h. So that's the approximation plus whatever little bit is the gap, is the error that we didn't actually get. And no, we can't really solve for the error, but we can try to estimate how big it is as a function of how many steps we use. So what we're going to do here is a Taylor expansion of the original function. And then we're going to integrate that Taylor expansion, and that's going to be how we can get our hands on the approximate size of the error. So we're going to actually do the Taylor expansion a couple times. And the reason I want to do a couple times is if we look at our trapezoid rule, I have two terms in here that I need to recreate. So the first time I do the Taylor expansion, I'm going to be doing it about the point x equals 0. So we're going to replace f of x with f at 0 plus x times the first derivative of f at 0 plus all the other infinite terms in the series. But here I'm just looking for like what's the dominant error term, so I'll just stop after 1. We'll do this again about point h, so that would be about the other side of the integration range. F of x is going to be equal to f at h plus x minus h times f prime of h plus ... all the other terms. And so looking back again up at the top where I have the rule, it looks kind of like I have an average. So like looking up here, we've got h on 2 and another h on 2. I mean, that kind of looks like an average there. So what I'm going to do here down in my Taylor series is I'm going to average the two of them. Kind of like the average Taylor series. So f of x is going to be equal to 1/2 f at 0 plus 1/2 f at h. And then looking at the next term, we'd have 1/2 times x times f prime of 0 plus 1/2 x minus h times f prime at h, and then so on with the other higher order terms. Okay, so now what I want to do is I want to take that Taylor series and I want to go and plug it into the integration and basically see what's left over. And that leftover part tells me what the error is, or it tells me the size of the error. So integrate 0 to h f of x dx, and that will be equal to 1/2. So we're looking at the first term, 1/2 times f0 times the integration 0 to h dx, because everything there was a constant. The second term, again, everything's constant, so I can pull out everything in front of the integration, 0 to h dx. Third term, that one has an x in it. So we're going to have a 1/2 f prime of 0, integrate 0 to h x dx, and then the final term, 1/2 f prime at h, integrate 0 to h, x minus h dx, and then plus ... Okay, and then if we evaluate all of these integrations, and they're easy to do, we get an h from the integration, so that gives me an h on 2 f0. Okay, that's good. That's kind of looking like the first thing in the trapezoid rule. The second term gives me actually exactly the second term in the trapezoid rule. And so then these other terms here, the stuff I'm putting in brackets is the trapezoid rule. Everything else must be the error. I'm going to get an h squared on 4 times f prime 0. And then this one's a little trickier, but we just do a quick u substitution. It's basically just going to come out negative. H squared on 4 times f prime on h, and then so on. Okay, so all this stuff here is the error, and that error is proportional to h squared. So we have h squared, and we have higher powers of h in that ... And h, if we're doing this right, is tiny. We're trying to make the spacing between points tiny, and so higher powers of h are smaller values and are less important. Okay, so the key thing here is our error scales like h squared. Let me clear the screen just to get some more space. Error scales like h squared. And since we know that h, by definition, is the endpoints b minus a on n, so I'm sort of jumping over to your generic. You have integration limits that are not necessarily 0 to h, but instead they're b to a. Each h in there has this size. So it scales like 1 on n. If we plug that in, that means that our error is proportional to n to the negative 2. Okay, so as we increase the number of points that we evaluate our integration, it's like 1 on the number of points squared that our error is dropping. So that's good. That means that we kind of quickly get more accurate as we add points. That's for this trapezoidal rule. We could redo all of that for Simpsons Rule. It would take longer because we would have to include more terms in the Taylor expansion. But what we would end up getting when all is said and done is the error for Simpsons Rule scales like n to the minus 4. And that's actually a lot better. So Simpsons Rule is kind of your sweet spot for this kind of approach. You can go to higher order, but you spend a long time not just deriving it, because somebody else could derive it for you, but like the code it takes, like the algebraic expression gets really long. It takes a while for the computer to crunch those numbers, and that starts slowing you down. So your sort of sweet spot Simpsons Rule at second order here, because your error is scaling like n to the minus 4. So does this mean let's just throw in a billion points and we're done? Well, there's a secondary issue when you're calculating values on a computer, and that's, remember that floating point numbers on a computer are not exact. You get rounding error for every operation you carry out on your computer because your numbers are truncated at some point. So for your computer, this will vary depending on operating system and exact version of Python, but most typically the precision of your computer is around 10 to the minus 16. And so if you make n so large that you're getting values that are a lot smaller than that, then you're just wasting your time. In fact, if you use too many slices, you can actually start to get nonsense results because you have just rounding error and you're creating an integration out of just rounding error. So if we plug in 10 to the minus 16 for the error, then solve for n, what we're going to get is that n's greater than about 10 to the 8 have no benefit for the trapezoidal rule. And that would be n's greater than about 10 to the minus 4 for Simpsons Rule. So since Simpsons Rule is not that much more complicated than the trapezoidal rule, And 10 to the minus, or 10 to the 4 points is not that big a deal for a computer at all. That's sort of your ideal for this style of integrator, is to have 10,000 points, use Simpsons rule, and you can get pretty accurate estimates for the integrand. Now there are ways for this to fail. If you have a really deviant function, you got some kind of function that's like doing this. Well, I guess it wouldn't really cross itself, but it's varying extremely rapidly, like between the points. Your integrator has no idea what happens in between those points. So there do exist functions that are just terrible to integrate, really in general, but especially with Simpsons rule and Trapezoidal rule. And there can be cases where the Trapezoidal rule actually beats Simpsons rule. Like that rapidly varying function, doing 10 to the 8 rapidly varying points with Trapezoidal rule will beat the 10 to the 4 widely spaced points with Simpsons rule. And so, you know, it's not that there's never ever a use for Trapezoidal rule or Simpsons rule. It's sort of a matter of you need to know what it is you're integrating in the first place. So like really step one should be plot your function, see what it looks like, then you can go about integrating it. So we just saw how many points you should use to carry out your integration. A related topic is how do we estimate the error in the numerical value we get out of the integrator. So suppose I carry out an integral, I get the answer 42. Is that 42 plus or minus 0.01? Is that 42 plus or minus 40? There's kind of a big difference. So what we're going to talk about right now is how do we estimate the size of the error. Suppose we run the trapezoid rule and we use endpoints. So then the situation is that the true universal truth value of the integral is not quite what we get. We get some answer, we'll call that I1 for our first attempt, and then there's some error E1 that we don't really know. Now we do it again. So it's the very same integral, but we use 2 endpoints. So we should get something more accurate. Still not exactly I true, unless by some coincidence. We get a different value I2 and a different error E2. And since we used more points, then we should be more accurate. Not only that, but I true is the same thing in both cases. So it must be that I1 plus E1 is equal to I2 plus E2, and E2 is more accurate than E1. Not just more accurate, we actually have some idea of how much more accurate. Because we know that the error is proportional to n to the minus 2, which means that E2, with twice as many points, should be better by a factor of 4. It should be equal to just 1/4 of what E1 was. At least in an order of magnitude sort of sense. So it's not exactly, because it's an error, it's an unknown thing. You can't say, well, it's exactly 4, but it's around 4. So that means that I1 plus 4 times E2, so we just replace E1 with 4E2, would be equal to I2 plus E2, and then we can solve this for E2. So E2 is equal to 1/3 of I2 minus I1. Again, this is kind of an order of magnitude answer. So like if you calculate the error and the error is 1.3, it doesn't mean, hey, I better just add 1.3 to my answer and now it's exact. No, it means that that's about the size of your error in a statistic sort of way. You mean your error, your true error might actually be 0, but you don't really have any way to know that unless you actually know what the integrand is, in which case, why are you doing it numerically? But it gives you sort of a sense that, like, statistically speaking, your error is around 1.3, plus or minus 1.3. As you might guess, we have a slightly better version for Simpsons rule. Better as in more accurate. For Simpsons rule, the way you calculate the error is take 1/15 I2 minus I1. Does that mean Simpsons rule is exactly 5 times as accurate? No. It's an order of magnitude sort of thing. You're going to get different values for I1 and I2 using a different technique anyway. But given those I1 and I2s, that's how you can calculate a number for your error. So we've seen that Simpsons rule should in most cases be more accurate than the trapezoidal rule. Let's write some code that's going to carry out that comparison for us. Let's use our widgets that we've learned about earlier in the course. So I'm going to import IPy widgets. as widgets. And I'm going to create some code that I want to compare. So I'm going to create some kind of function called compare. I'm going to give it endpoints to compare. So we'll do like Trapezoid Rule with endpoints versus Simpsons Rule with endpoints. And then we're going to put some code in there. But just to outline some things, I'm going to make a slider. And I'm going to make a GUI that's equal to a widgets.interactive. And then I need to display that GUI. And then I guess to be able to display code, I need to make sure I've imported that functionality. So we're going to do from IPython import display. Okay, so I should we got our bare bones here. Now, as far as like what is it that we're going to compare, let's come up with some kind of function to integrate. So let's put that, I'm just going to make an extra cell up here. Let's make that a markdown cell. We can type some math in it. I'm going to put my math here between double dollar signs. It makes it formatted nicely. You don't really have to worry about learning how to do the formatted math markup. But what I want to do here is I want to evaluate the integral that ranges from 0 to e, the base of the natural logarithm. And the thing I want to integrate in here is the natural log function of x. Put a nice little space in there, dx. Okay, so that's the math I want to evaluate here. And that integration, if you work it out by hand, should give you a value of exactly 1. But it's kind of complicated. And the reason I picked a more complicated function than like x squared is because it's not a polynomial. It's not a nice smooth function, and neither trapezoidal rule or Simpsons rule can actually do this problem exactly. They're both going to be estimates. So up here in my compare function, I'm going to create a bunch of x values because the trapezoidal rule and the Simpsons rule that live in SciPy like to work on arrays. So they need an array of x values and an array of y values. Typically, the way you get your x values is with a linspace ranging from the lower limit to the upper limit. So let's do, all right, I typed the wrong lower limit. This should be a 1. Because natural log 0, of course, is negative infinity. 1 to e. Anyway, my lower limit here is going to be 1. My upper limit is going to be e. I can get that by calculating the exponential of 1. And let's do a total of n steps there. Okay, so we're going to compare n steps. In each of these, I need to generate n steps as we go. Of course, n needs to be at least 2, or else this function call will break. But it's also kind of silly to try to do an integration with a single point. Now we're going to calculate 2 integrals. We'll call them I1 and I2. I1 will use the trapezoid rule. So we're going to do integrate.traps. And we're going to call that on log of x with respect to x. And then we can just copy this code. It'll be exactly the same, except we'll do Simpsons rule. So I'm going to call that I2, and I'm going to call Simps. Okay, so then each of these integrations will be carried out using n data points, which is what I passed to the function. Now we need to get our results out somehow, so we'll just do a simple print statement in this case. So for the trapezoidal rule, for traps, just print out I1, and for Simps, we'll print out I2. Okay, so that's my function. Now I need to make a slider here for my n values. So we'll do a widgets.slider. Sorry, not slider, it has to be a type of slider. So it's going to be int slider because n has to be an integer. Let's go with at least 2, and we'll go up to 100. Okay, and then in interactive here, the function I'm calling is compare, and I want to set its argument n equal to the value I get out of my slider. So unless I made a typo, I made a typo, of course. Display module not, sorry. My bad. So I imported the display module up here, and the function to display is called display. So it's sort of it's a double here. Display.display, display module, and use the display function from that module. Okay, so with 2 data points, it looks like we've got basically the exact same answers. But as we start increasing the number of data points, we start to see that the values differ. And the answer is supposed to be 1. So we see Simpsons Rule is winning here. We go out to maxing out here at 100 data points. So it's a nice interactive way to check the accuracy, and it gives us an excuse to use our widgets. We could calculate a similar sort of comparison just with a straight up for loop. So we could do for I in range 9. What I'm thinking here is we're going to do like 10 to the 9 data points. A lot more than you'd want to do with a slider. We've got our x values up here, right? So we can just copy. Actually, we could really copy like all this. And instead of doing n, though, I want to do 10 to the power I. Okay, so like I will start at 0, and that'll be 10 to the 0, which is 1. So actually, that would be a problem. I guess we need to start here at least 10 data points. So we'll start here with 10 data points, and then the next would be 100, 1,000, and so on, up to 10 to the 8, 1 less than 9. And so we're going to evaluate the two different integrations, and let's print them out. So let's use an F string here, because what I'm picturing in my head is a little bit fancier than I could do with just a straight up print statement. So I'm thinking here that we're going to print something like n equals, and that would be like 10 to the I. Use this curly braces here, so I'm going to plug in the value I so that it appears literally in my text here. And we'll make a little colon here, and we'll do like the traps equals its value and simps equals its value. For traps, we're going to want to show I1. For simps, we're going to want to show I2. And let's make sure we're showing a lot of decimal places. I think by default it will show a lot of decimal places, but let's go explicitly 16 decimal places. So 0.16f added here as some formatting for each of these. All right, let's run that. So we can see it's actually taken quite a long time to do 10 to the 7. It's not done yet. It's still working on 10 to the 8, but it takes 10 times longer than 10 to the 7. Telling us something important here, that running with a bajillion data points blindly is not a good idea. It's a really kind of poor idea. Furthermore, we're not gaining any more accuracy. You know, once we're up above, say, I don't know, what was that value we just calculated in the previous part, 10 to the 8 for Trapezoid Rule? There we're gaining values, but like here, 10 to the 4 for Simpsons Rule. Let me highlight here. That's sort of like, that's the best. And we're not really gaining anything going above 10 to the 8. You know, we're out here like at a lot of decimal places, and we're just not really gaining anything else. So it's not worth using more than 10,000 decimal places, 10,000 steps when doing Simpsons Rule. You just don't get anything for it. Also showing us why Simpsons Rule is typically preferred. 10 to the 4 runs literally 10,000 times faster than 10 to the 8. And that's what you need if you want to max out your accuracy in the Trapezoid Rule. But if you give it enough steps, Trapezoid Rule will give you a very good accuracy.